Back Chemistry 30. So this is the third video in EQ1.6. We looked at changes in concentration, changes in pressure, volume. Now we'll look at changes in temperature. So we can think of it like this. Some reactions produce heat, in which energy is exothermic. So this is like in Physical Science 20, we learned that exothermic reactions have energy released, which means it's going to be on the product side. If we consider heat like a reactant or product, Le Chatelier's principle says that if we add it, the equilibrium will shift to the left. If it's lowered, it shifts to the right. So we think of heat as an actual item. But of course it isn't an actual item. So what happens here is that it does affect the equilibrium constant. Because since I'm actually not increasing something at the start, if I'm causing it to shift in some way, it will cause changes in the equilibrium constant value. Because remember before, if I increase concentration or decrease, it doesn't change KEQ. But back then we were actually adding something. Here we're not. We're just simply lowering or raising the temperature. Okay? So if we imagine it like this, there's heat. If I add more heat, think of it as, oh, it's increasing on the right-hand side. I need to shift things to the left, so move this way, this way. This will increase, this will decrease. And of course, KEQ is concentration of products over reactants. So if I'm using up, so if I added heat, and if things are going to be making more reactants, this is going to increase. Making more reactants means products are getting used up. So if I have a smaller number divided by a bigger number, of course, that results in a smaller overall value. Vice versa, if I remove heat, so remember, it's like someone jumping off the teeter-totter. So if I take this off, it's getting lighter, getting lighter, getting lighter. So I'm going to want to shift things to the right. Shifting things to the right will make more products. And shifting things to the right means using up reactants. So in other words, I get a number that has a bigger number divided by a smaller number is going to make my KEQ value much bigger. Okay, so that's kind of the rationale there. It's very similar to the concentration changes, except actually we're not increasing the amount of something. So if we're causing it to go in a particular direction, the KEQ value will in fact change. And of course the opposite is true if it is endothermic. So endo, it's like saying enter, energy entering. So it's on the reactant side. So Le Chatelier principle suggests that if the temperature is raised, so if it's raised, it's getting heavier on this side, it's going to shift to the right to use up. So it shifts to the right, which makes a bigger KEQ value. And if energy is removed from an endothermic reaction, so you can see here it's on the left-hand side, taking it out, it's making it light on the left-hand side, so things are going to want to shift to the left. So temperature lowered is the same thing as taking it away. It'll go to the left, making reactants bigger than products, so my smaller products divided by bigger reactants will make this smaller. All right, so generically, let's take a look here. Again, the key here is to treat, hint, treat temp or heat, loosely speaking, as a reactant or product that is added or removed. So stress, if we increase heat. The response will be to try to decrease heat. So shift to the side that uses up heat. Of course, if it's endo, that means going this way. If it's exo, that means going this way. Because remember, endo is a reactant. Using it up will make it go to the right. Exothermic energy is on the right, so it's going to go to the left. And then the usual here. Side shifted to will increase. And then side shifted, yikes, away from will decrease. All right, vice versa. If the stress had been to decrease heat, that's like removing it. The response will be to try to increase it again. And then that means a generic shift to side that replaces heat. So if we're talking about an endo term, the energy term is on the left-hand side, so it's going to try to replace it by going this way. If it's an exothermic, remember heat is on the right-hand side, so things go from reactant to product with that one. And the usual here, side shifted to will increase. And then side shifted away from will decrease. So that's how heat works. And of course, we'll see exactly how this works when we look at an example in which we have all these factors coming to play. All right, so let's take a look at this example. So here we'll have a bunch of these coming into play. So here's our heat term. Okay. So each of the following, we have the stress. So you're given the stress. So what is the response? Which direction does it shift? And then what increases and what decreases. Now I can try to give you that template at the start. So over here, we have an increased amount of CH3CHO. So let's find that. So CH3CHO. CH3CHO, there it is. So if it's increased, so that means an increased amount means like it's like a bunch of people went on the right-hand side of that teeter-totter. It's going to look like this. So here's my CH3CHO. So if I increased it, it's going to cause it to go out of whack. So if our stress was increased amount, we want to try to do the opposite. Use up the extra concentration. I'll use the square brackets here to mean concentration of. So use it up. So in order to use it up, we of course know to make this go back into balance, from your experience with teeter-totters, we want to move to the left. Shift to the left. And if I do that, it'll look like this again. Okay? So if it's going to the left, the things that the reaction is making, it's pointing in the direction of reactants. So reactants will increase in concentration. And we're moving away from products. We're using up products, so products will decrease. Sometimes for concentration, I just like to do square brackets, indicate that that means concentration. All right, so concentrate. Here's another concentration amount. decreasing C2H2. Let's find C2H2. There it is right there. So if we're decreasing it, it's like it's being pulled off. It's like it's being removed. And if I remove something from the left, it's going to go up like that. So let's maybe just sketch that over here. C2H2. So we're removing some. So their teeter-totter is going to be light on that side. So if I remove something from the left, just like a teeter-totter, we still have stuff on this side which is going to pull it down. So decrease. So the opposite of decrease is increase. Try to increase the amount of C2H2 again. So of course you can see the teeter-totter looks like that. So that means things are going to try to shift this way towards reactants and away from products. You're always shifting to the side that's lighter. So again, we're going to the left. Reactants will increase. And products, whoops, let me actually take a look at this. Products will decrease. All right, we'll stop the video there. We'll look at the next side in the next video.